Thanks everyone for coming again. I think we have one more lectures to cover everything except sheaf cohomologies. And I don't know how much topic I can cover, but I'm trying to explain some main ideas, right? And by the way, if you have any questions, let me know. Sometimes I speak, I forgot to ask you for questions. If you have questions, please stop me. So the idea coming from look at this category, right? It's a beautiful category, and everybody wants to generalize it. So there are two ways to do that. First is do the ring theoretical way, sort of doing non-commutative rings. That's the forbidden path we cannot take today because we're talking about algebraic geometry, so non-commutative. But there is an algebraic geometrical approach, right? The idea is consider its opposite category, and the opposite category has a geometrical favor. Especially for commutative rings, it is same as the affine scheme category. Now, one lazy way to understand affine scheme categories is just say it's the opposite category of commutative rings. It doesn't make too much sense because it means that you don't know what geometrical is. But categorical speaking, that is same as the opposite category of commutative rings. And the functors may be also important is how you're going to associate these two categories. And at the same time, you kind of understand how to construct this so-called affine schemes. So if I give you a ring R, I have to assume it's commutative, otherwise it doesn't make sense. The associate object in its opposite equivalent category is a affine scheme. Hello, Guangyu, nice to see you. And it's actually a locally ring space. So what you do is you associate a topological space called the spec R, and same time you associate a ring of structure sheaf. So this is a topological space with a structure sheaf. And the morphisms in that category just match with the morphisms in the commutative ring. So to speak, if you have a morphism between two affine schemes, S, OS, and you say a morphism defined is that it's always only coming from the opposite maps from the corresponding ring. So this is delicately done so that these categories are literally equivalent to each other. But in order to make it this morphism a little bit more independent, you have to consider this as a special case of locally ringed space. But we are going to see it later, so I just gave you the idea how to enlarge this category to affine scheme. Now, in the idea that finite generated domains is a subcategory of commutative rings, right? And the corresponding subcategory of affine scheme rings are called integral. Over base field decay. So actually the original idea of defined affine schemes are coming from the classical geometry from these finite general domains, which called affine varieties, right? So for affine variety, you associate the coordinate ring, you get your finite general domain. And what affine scheme does is to generalize this to commutative rings. But in this side, you're not only having finite general domains, sometimes you have a more general case called a projective scheme. Or coming from commutative rings, a graded commutative ring, we call it project R construction. And in the classical sense, it is a projective variety. And so we can further enlarge this category into the so-called the category of schemes. And this is all in the level of locally ringed space. And one way to define schemes is locally isomorphic to affine scheme. So it has open covering or open basis, which every basis is isomorphic to affine scheme. And then you group them together under some transaction functions, which everything should be taken as locally ring space morphisms. And if you are being a little bit general, you can even embedding this to the category of topos. So that's one way people do. And as I said, there's another way to include this by stacks. So you can also do that. So now, so this is the categorical level. We understand what this algebraic geometry is. We didn't do too much, but at least we know the category, right? We're starting with this category. We can imagine the finite generated rings. And we kind of like ends up with a very gigantic, bigger category, which includes more stuff. And the category schemes is the middle of it. Okay, so the next thing I'm going to do, which we're trying to link to what we are going to learn for next week, is the Schiff cohomology theory. So we still want to give you some comparisons between category of schemes and category of commutative rings. So there are basically three ways. No, there are many ways, but I'm just quoting three ways to understand the category of commutative rings, right? Maybe the easiest way we can imagine is a classical representation approach. The basic idea is to understand the modules of commutative rings. And also, based on that, people develop homological methods and also others. I mean, others and maybe categorical. These are gradually abstracting. So coming from this concept of modules, people doing homotopy theories, then later doing categorical theories. And the main idea behind this is you have a category associated to the modules. So if you give me a commutative ring, I can associate a module category mod R. Sometimes you have two of them, capital mod R and little mod R. Capital mod R is all modules. And little mod R are those finite generated. And this is another category which build up from the category of commutative rings for each object. And these categories has very nice homological characteristic you can study. So at least they are so-called abelian category. So one thing you can have abelian categories, you can talk about exactly sequences and also build up about exact sequences, and you can do all sorts of derived functors or homological methods, right? So that is how you do in the category of commutative rings. And there's another level is you can do the derived version. So which you take here. So this is kind of one different level to do that. And the benefit of that is the derived category forgets all sorts of annoying things which we focus on the cohomologies only. So this is people usually do for representation theories for commutative rings. And I want to remind you a reconstruction theory, maybe that might be interesting, is so-called Morita equivalence, right? So one thing that if you're starting with a commutative ring, you can build up an abelian category, which captures the properties of R. But one question is that capture all the information of R, or you kind of like can reconstruct R? And this is coming from the classical Morita equivalence theory. So for commutative ring only, if you have a Morita equivalent between these two categories, then R has to be isomorphic to S. It's classical. Now it doesn't work for non-commutative rings. For example, the matrix algebra is Morita equivalent to the base field K. So it's not. But as long as you stay in the safety of your commutative ring category, this abelian category, the representation category uniquely determines R. So instead of talking about rings, you can completely talk about abelian categories. That would be good enough. I don't know if there's a derived version. I guess you do have something else. So I don't know if derived categories recover that. I don't have a chance to look, but I suspect it may not be. This is no.
I mean, in general, if even if R is not isomorphic to S, you can have mod R being isomorphic to mod S, which would imply that derived category of modules on R is the same as derived category of modules on S, but of course,
So
R
derived
is
does not recover, right?
Yeah, I mean, it's there's things that were Morita equivalent. Sorry, if you're Morita equivalent at the abelian category, you'll automatically be Morita equivalent at the derived level, but it doesn't go the other way around, right?
Mm-hmm.
You can have some exotic T structure.
Mm-hmm. Yeah, so this is good, not good enough. But there's a way to recover it. That's my point is nowadays people studying these so-called tensor structures. So if you add the tensor structure, insist these two derived category isomorphic as triangular tensor categories, then there's a theorem. I think Bohm or something can recover it. Or Bohm in the late. So you can recover that, but you have the most structures. So now
I think you'll see the fiber functor, but yeah,
something
like that, something like Chinakian type formalism.
Thanks. Yeah. Now I'm going to do the same story for this category, which is definitely bigger than commutative rings, right? So if you have a scheme, can you associate a abelian category, which you can kind of like recover all the thing, which you can do the equivalently, and also we can talk about the derived versions. So actually, there is a good candidate already there. It is if you give me a scheme, I can consider its quasi-coherent sheaves. That serve as the big R big model R, and also we have a subcategory coherent sheaves X, which serve as the finite general module versions of this. And there's a theorem called the Gabriel Rosenberg reconstruction theory, which tell me that if two quasi-coherent sheaf categories are equivalent as abelian category, then it uniquely determines that the two schemes are isomorphic in the category scheme. So this means that we can do the same trick even we enlarge it. I don't know if we can do bigger one like for stacks or something, I have no idea. But for schemes, we can do it. And we can talk about a derived version. And same thing, we cannot completely reconstruct it from derived version. And it's not possible unless we need some extra structures. Okay, and the interesting thing that this is also an abelian category. It has very natures a little bit different from the abelian category we get from representation categories, but it has enough information we need, which we can do cohomologies. And that's why we can form the derived versions to simply focus on cohomology.
Sorry to interrupt.
Mhm.
Sorry to interrupt. For the reconstruction thereon, I'm confused. So should this have some conditions on it? I don't know what kind of conditions.
Yeah, separated. Yeah.
Separated. Okay.
Yeah, but I'm not trying to put them more. Yeah, you do need some construct separate. Quasi separate. Okay, so now we are trying to learn this category a little bit and trying to understand why this category can be served as a representation category of schemes. So first, I'm doing a limited general instead of talking about schemes. Actually, we can define for any locally rings. So suppose you have a scheme and you have a structure sheaf, then you can associate this quasi-coherent sheaves effects. Now the things we have to do is we do need to go back to a little bit definition of what sheaves are, and probably I have to mention a little bit if you are not quite familiar with. I'm not going to give you the precise definition as I did last time, but just give you some concept for understanding it. So if you have a topological space, you can define sheaf on it, and sheaf is the best flexible machinery which you can capture local data by talking about things on it. So a sheaf on X is, roughly speaking, there are two ways to understand it. One is look at étale spaces. That's a topological way, probably much earlier than the Grothendieck functorial view. So you can consider as étale cover of spaces over X. So you have étale space X, and the étale space means that locally is homeomorphic. And the other way is to look at as functors, but you have to say sheaf of what, right? Usually sheaf of sets, but for schemes, it's usually better to look at a sheaf of abelian groups. So you can look at as functors from the category of topologicals open set categories of X. So this is a category built out of X. The objects are open sets. Morphisms are open sets inclusions. And the sheaf of abelian groups means I'm talking about functors from this open subsets category of X to the category of abelian groups. And if you have this, it's called a pre-sheaf. Then you have to do some like the section are determined by local data. That's called a sheaf property. So it's a functors from top S to abelian plus some sheaf properties. And these two turns out to be equivalent. So I talk also a little bit about how to associate between them. So if you have a Étale space, I can find a functor by looking at the sheaf sections. And backward, if I have a sheaf from the top to abelian, I can recover the Étale space by looking at the stocks, just grouping together by some minimum quotient topology on that. So okay. Stocks. And this gave us a objects. And we also need to talk about the morphisms. So if you want to talk about morphisms, you can define morphisms in two ways. In the functor way, the morphisms is basically natural transformations. That's why this functor way makes things easier, because it's easy to generalize. But you also can define morphism by morphism between Étale space, which respect to the basis. So you all can define this. They are all equivalent. So this become a category. And we also need to know that the functors between different sheaves are different topological spaces. So the basic idea is if I have two topological spaces, X, Y, I have a morphism between them, I'm going to have a pair of adjoint functors between their sheaves. Called push forward and pull back. And for pull back, there are two notations, which is very, very confusing. First notation, which you only talk about sheaves, not quasi-coherent sheaves yet. You're gonna attempt to use F inverse one. But in the quasi-coherent sheaf level, you're gonna have F up star. So this is reserved for quasi-coherent sheaves, and hopefully people won't get confused. So we only talk about space yet. So that's why I put this. And they are adjoint to each other, which means the push forward is the right adjoint for the push back. So how to define them, that's also very interesting. So the most natural way to define push forward is using the idea of functor views. And the best way to define the push back is using the Étale space level. So let me explain this. So if you want to suppose you have a sheaf on X, so you can push it forward by applying this continuous map from X to Y. You're going to have a sheaf on Y. Now, in order to define sheaf on Y, you can either use the Étale space description or using the functor description. And it's easier to view it in the functor description. So what it means that I'm going to have a functor from topological space open subsets of Y to the abelian categories. And this ways means that if I give you open set of Y, I'm going to get an abelian groups and satisfy these by functorial way, sheaf property, but that's we'll check later. But from the functorial way, if you give open set of Y, how am I going to get an abelian group? You know, F signs open sets on X get abelian groups. So one natural way to do it is pull out this open set. So it'll be F inverse, right? And that's a lot of things for us to to check is this is a functor in respect to the restriction. So if you have restrictions, open set inclusion, then you're gonna have restrictions, which is very natural from the previous functor property. And you also need to check the associativity, the sheaf property, which is also can check. So that's how you define push forward. You just do the inverse functors, kind of like this. Now, you also can do pullback, which means that if you have a sheaf on Y, you can get a sheaf on X. But this way, it's you can define from the functorial way, but it's kind of like become a little bit tricky. So the way to see how you define the pullback is using the pullback of Étale spaces. So as I said, there are two equivalent ways to define sheaf. So having a sheaf on Y is same to have a Étale space locally homomorphic to Y. And how you're gonna do the pullback is you just take the pullback in the topological spaces. So, and it's easy to see that in this way, this is also a Étale, map on an Étale space of X, because it's also locally homeomorphic. And one more thing is that it doesn't change the stocks. So if you have a fiber on Y, then if you pull back, the fiber stays. So that's another thing very important is pullback doesn't change stocks. So I'm going to define this F G to be the solution with a pullback space. Okay, and also you can check that they are joined to each other. So F G. There's a natural isomorphism between the homes. And one consequence about this adjointness is the push forward is always left exact, and the pullback is always right exact. Actually, there are more to say. It's actually this is exact. Why it's more than right exact is because, as I say, if you view this pullback as Étale space product, and that you don't need change the fibers. So and the things keep fibers just mean that it's actually preserve stocks or fiber. Okay. So this is what I trying to see, the functoriality of sheaves. Then we go a little bit further. How about we don't only have a topological space, but actually we have a sheaf, a scheme. Now I want to define a represented category of schemes. The bigger one is called quasi-coherent sheaves on X. The smaller one, which like finite general module versions, is called coherent sheaves on X. Okay, so the way to do that is only consider the very, very nature property of schemes. Now, I'm not going to give a general definition because it has a lot of checks. So I'm going to give you a complementary, complementary version of that, which is easy to remember. So one easy way to remember schemes is that they are locally like affine schemes, right? So if you locally speaking, you have open covering of a scheme, which locally is like spec some ring I with a structure sheaf O. Let's say O spec I. So the very nature about quasi-coherent sheaves or coherent sheaves, they're actually sheaves. So what the sheaf property which is satisfied means that these informations are completely stored in local data. So if I can tell me all the information on the local data or the affine covers and tell you the transaction functions, you can completely recover the sheaf. So what a tricky way to do that is I don't know what it has on every open set, but I can only define on these affine open covers. So in affine open covers, these are exactly these modules. So now certainly you have to worry about these transaction functions. So if you have mi, then you need to have these theta ij's, which give you transaction functions. Say this is say ui. You need to do ui intersect to uj, then restrict to uj intersect to ui. And you have these two co-cycle conditions which compatible with the transactions. But that's how you get a quasi-coherent sheaf. So basically on affine set, there are modules. And you make this module into sheaf by doing localization. So localization. And you also need to tell me the transaction functions. Now, if you do not have any restriction on the module side for each open cover, that's called a quasi-coherent sheaf. If you require at least on one affine covering, all these MIs are finite generated, and this become a coherent sheaf. So that's the difference, just like capital M mod R and little mod R. It's just whether in these local affine data you want the arbitrary modules or finite generated modules. Yes. Okay, so now this we give the objects. So what are the morphisms, right? So the morphisms, if you have two quasi-coherent. So what are possible morphisms between them? And that's very easy to define. What you want is a collection of module maps, which module from every mi to ni. It will be Ri module maps. And also these module maps are compatible with these so-called transactions, which are compatible. Transaction functions. And that's the way how you define morphisms. You just need to have morphisms on each affine piece, and they are compatible with the transaction. So you can group up them together into at least a morphism of sheaves, also compatible with the structure sheaf actions. So this is give us the category. There are many things which are interested in about this category. And I want to give you some observations because you need these property to run out this sheaf cohomology theory. If you don't have sheaf cohomology theories, probably there's no way you look at them. So observations is first is this is actually both quasi-coherent sheaves or coherent sheaf categories. R is abelian category, just like module categories. And that's why probably the word abelian category is invented, because it captures two main sources of representation categories, one from commutative ring, non-commutative ring, the other from sheaf cohomologies. And it's very good to unite them together under the name of abelian categories. And also another thing which very crucial to forming the derived category is whether everything has enough projectives or injectives, right? So that's a very good question. So can you form the derived category? or bounded derived category. And not every category can do that, because you have to have the homotopy category. Then you have to model out all the quasi-isomorphisms. You can do it, but you need some better ways to make this construction nicer. And usually under two conditions you can do it. Either every object has a projective, has enough projectives, means you can do projective resolutions. Now the sheaf category doesn't work, so this will not work. And that's quite different from the ring representation category. One thing you probably will learn from ring categories, which I mentioned earlier, is it has both enough projective or injectives. And projective resolution is much better if you want to compute the X groups. So if you have projective resolution, things become a little bit computable. Bad thing for this is for category of coherent sheaves, I mean, it is a abelian category, which is good. You can form exactly sequences, but there's no way you can form project resolutions. But good thing that it is an example of so-called Grothendieck category, which guarantees that has enough injectives. Means you can form injective resolutions. Every object can be resolved by quasi-isomorphic injective complexes. So you can form the derived by taking injective resolutions. And one thing which very nature associated to the functor we just talked about is the push forward. So one thing about having inject resolution is you can do so-called a left derived functor. You just take injective resolution and apply the functor to the inject resolution, take cohomologies. And it works for any left exact. So the things which we'll see a lot in the so-called the sheaf cohomology theory is you're going to compute some of the push forward functor, which I'm not going to talk. So next week, I think Guangyu will tell you a lot about computing these cohomologies. I'm just telling about the foundations for him so he can run easily. Okay. So that's the representation nature of quasi-coherent sheaves of X, coherent sheaf X, and how you can form the derived category because they have enough injectives. And now we are going to talk about the functors. We talk about the sheaves. Is suppose you have a morphism from X to Y. Here you are talking about in the sheaf category or skin category. Let's keep speaking on the right. And you sort of should have the same pullback, pull over between the quasi-coherent sheaves, right? So similar as the category, you're going to have two functors. One is called the push forward. And the other, which has a different notation, is called pullback in the category of quasi-coherent sheaves. So this definition is same as we did in the piece called same as in the topological. You just take the functorial point of view and trying to pull back the open sets. And it's very easy to see you land up with the quasi-coherent sheaves. This is a little bit different, so it's not the same as this. The reason is if you define this definition, you sort of like doing the pullback of Étale spaces. But the Étale space pullback doesn't guarantee the pullback is indeed a coherent sheaf. It's a sheaf, but it may not be a coherent sheaf. So that's a bad thing. So this is a sheaf on X, but because it's a Étale space, but it's not a coherent sheaf because there's no natural OX action on this. So this is kind of like fixing it. So what it does is I'm first taking F of let's say G, then I tensor with Y and OX. So I don't know how to say that, but my understanding is like trying to form a OX module structure on that in the best non-harmful way, so you don't modify it too much. And one thing about this definition, you still have a joint functors between them. So this is quasi-coherent. You still have a joint pair between the pullback, push-up in the quasi-coherent sheaf level. And as a consequence of the joint functors, this is still left exact. So you can talk about the derived functors of this pullback, and this becomes left exact. I don't think it's exact, but this is left, this is right. This is left. I don't want to. So you can take left derived functors. So that is the very beginning of taking sheaf cohomologies by understanding the representation category and the functors between them, especially these left exact functors, right exact functors. And you can define the cohomologies in the Grothendieck way. So you can define cohomology theory using there are two ways. One way is using so-called derived functor versions. And there's another way, which is more fancy. I have never know you can do it in the derived category. Then the derived function just be named X or Rx. You can do that too. Okay, that's not what I'm trying to say because I don't know cohomology theory. That's the best thing I can know. So for later, I'm going to give you some examples for the rest of time, so we can at least play a little bit about the quasi-coherent sheaves. So what I'm going to do is give you two results, very fundamental. First is Grothendieck's splitting theory. Basically, his categorification of vector bundles are Riemann surfaces. And the other is the Riemann-Roch theory. I don't know if I have time to cover all of them, but maybe mention a little bit. So Riemann-Roch theory needs a little bit of cohomology, but the statement you don't need it. And I'm not going to prove neither of them. Actually, both of them needs cohomologies to prove. But I don't know how to prove because we haven't learned. But I will just state the result. So you'll see. So for first theorem, I'm going to say is analogous of modules of a PID, which is very interesting. Or we can do modules of Dedekind rings, but probably PID is good enough. So in the first year of abstract algebra or the second year, we all learn this beautiful theory of module structures of PIDs. What do we learn is if you have a finite general module over polynomial rings, one special example of PIDs, then it has a very, very nice decomposition theory, right? So it's always a direct sum of free modules plus and or these torsion modules. And the torsion modules has a very special form. Actually, it's only stacked in one point in an algebra way, which is kx over x minus some point to the have some, this is called the thickening, or called the ramification m. Okay, so that's a very beautiful result, and we use a lot. Now let's think about the Xi version, which is Grothendieck splitting theorems. Is we know we have this wonderful for enlargement of categories. Community rings are now embedded in schemes in the opposite embedding, I should say. And we know modules of community rings is sort of like representation categories, abelian categories. And in the same way, for scheme, we can talk about finite generally. So I'm talking about coherent sheaves, right? So if you consider this at, sorry, this somebody's calling. If you consider this, let me see if I can go back to my, okay. If you consider this theorem as a result in this level, you should expect there's a similar theorem on this level, right? As long as you can find the right analog of the affine line. This is the affine line, right? And you should have the same thing. And the base object you can think about is its one compactification, which is P1. And probably we need the field to be nice over C. So it should be a result which is stating that what are the coherent sheaves look like in P1C. And that's what exactly Grothendieck did. So actually the simile is very similar. So first I'm going to review a little bit about P1C. So how to view its affine basis and the transaction function. It's the easiest example, so and that's I think we better do it because I don't think it's too hard to do. First, if you have a project line that only two affine covers, actually you can prove every smooth curve has two affine covers by taking a projective morphism to P1. But here we only do P1. Actually, you can prove every smooth curve has a two affine covers. But here we do P1. So has a two affine covers. And because the gluing data are one, probably I use you use parameter Z, the other use parameter Z inverse. So this is actually the spec of KZ. And this is using spec KZ inverse. The reason I'm using inverse is because it's easy to restate that transaction functor. So that gluing together under some open set. So open set is exactly the spec. You localize that as the inverse, Laurent series. And this is also happening. And the transaction is identity. If you use Z here, you have to map Z into the inverse. That's bad, so I'm using the inverse.
I think the inclusion are reversed.
Oh, yes, you're right. Thank you. Yeah, right. How to say? Which way this? Yes.
The other way. I think the other way.
The other way?
Localize, yes. You're localizing some functions, so
yeah.
the rational point on it just get less. So
okay, yes. Okay, now let's think about what are the quasi-coherent sheaf or coherent sheaves data, right? So in order to have a coherent sheaf data, what I said before, you need to have two modules, one module of this, one module of this, and you have give me the transaction map between localization. So any coherent or quasi-coherent sheaf on P1 is given by every coherent sheaf is given by two modules, M1, M2. M1 is a module of KZ, M2 is a module of KZ inverse, and an isomorphism, say theta 1, 2, which basically you localize this module at Z inverse, and there is a isomorphism of the Laurent polynomial modules over this M2, M1 localized at Z. And this is the localization, so you can understand as KZ over KZ inverse. And this is M2 KZ inverse. This is okay. So any quasi-coherent sheaves is given by M1, M2 with an isomorphism of Laurent series modules. And coherent just means that M1 is finite generated, M2 is finite generated. Now let's look at some examples, which is interesting. First, I'm introducing the stereo twist sheaf O minus N. So what is this? Is I'm taking both M1, M2 as modules. So it's KZ module. M2 is KZ inverse 1 module. So they're locally free modules. These are called invertible sheaves or called line bundles. So locally is rank 1. And the transaction is not trivial. If transact trivial, it will be O0, the structure sheaf. I want to have something to do with this, so the transaction is multiplied by Zn. So what you do is this one, if M1 is trivial, it's just this, right? So if you take identity, that will be O, structure sheaf, and multiplied by Zn. And this gives you another not isomorphic inverter sheaf O minus N, and N can be NH. Okay, that's one thing. And also you can do the so-called the align bond associated to a wild divisor. So actually take a point in P1, you can define minus NP. And this one is actually would be isomorphic to this, but I'm going to do this. It is so I'm going to define that as a subsheaf of the canonical sheaf O, which is O0. So O0, you know, it is KZ identity, right? I'm going to add a subsheaf. So for each of this, I'm going to define as, so suppose P is a point. So I'm going to define Z minus the point to the power N, KZ, and this is to be Z inverse times alpha inverse N case. And the transaction is identical. It's very easy to check that these are the same because I make this alpha inverse. So if you take the localization, it just differs from some power of Z. So there should be exactly the same. So this is a subsheaf. This, if you look at the PID theory, it looks like this module. Okay, so what I do is I'm going to take the quotient of this, O quotient of the subsheaf, which I denote by OMP. And this is actually serve as a torsion sheaf. Okay, so now I can state the Grothendieck splitting theory. So what is Grothendieck split theorem says is, maybe I should say here, it's too much. So Grothendieck. Says, suppose I have a coherent sheaf on P1. Then just like we did in the PID case, it is a direct sum of the following modules. Either the zero twist ON with different ends, so maybe NI or AN, the torsion sheaves O, N, P. And this serve as the free modules, and this serve like the torsion module. So this is one result I think might be interesting to know, which is generalization of the PID structures about the coherent sheaves on the P1. They only can be the line bundles and also the torsion modules at N multiplicity at the point P. The next result I'm going to review is the Riemann-Roch theory, which has a very, very rich history, which I have no way to do that, but it's talking about dualities on curves. So I make it easy, that general versions. So what I do is I have to say a little bit about divisors. So suppose X is a smooth projective curve. Smooth is very important because what I do is I have to apply canonical sheaves, but I'm not going to talk about that. Then you can define the divisors, DIV. So it's basically formally the sum of points with multiplicity in Z. And for each divisor, I call it is effective. I use this notation. means all the coefficient is actually lies in Z. So it's all the Ni. Are non-negative. That's called effective divisors. Okay, so the next thing is some notations. So suppose you gave me a divisor. I can talk about the global. Actually, this is the global sections on the line bound associated to D. If you like, use cohomology, but we can complete do that. It's all the function field on X, which if you add the principal divisors to D, is effective. It's the space, the dimension of the space spanned by all this. So this is called a principal divisor. Which basically to capture the poles and the zeros of S with multiplicity. Right? If you give me a rational function, I can compute the poles and the zeros on the curve, and I just record these points and the multiplicity. It's positive, then it's a 0, negative means poles. And they're only finite, so it's well-defined a divisor called the principal divisor of X. And this HZD is taking all these rational functions, which its principal divisor and the original divisor is effective. So which means that the poles and the zeros are controlled by the point of D. For example, if D is a single point P, then this space is basically all the rational functions only allowed to have one pole at P. Every other you don't have poles. And you count all these vector spaces and count the dimension. And there's a result about the serial finiteness theorem. It says if you get a projective curve, actual projective variety is smooth, then this number is always finite. It's actually the global section, the first cohomology zero form a group of a coherent sheaf. So serial finiteness theorem tells it's always finite. Okay, so and also I need one thing, then we can done. It is so-called canonical divisor, which I don't want to say. It is if you know non-commuted geometry, you probably know it. It's like the how to say rigid dualizing complex, something like that. But I'm not going to say. But canonical divisor. It's associated to the canonical sheaf, basically the Kähler differentials. It's a line bound. It's called a canonical sheaf. Okay, so the Riemann-Roch theory gave us the relations between H0 and for any divisor. If you do this, so and the number is computed, the genus of X plus the degree of D, where degree of D is the sum of all the coefficients. Okay, this is a very important result, by the way, and because people can use it to do all sorts of classifications. Like you can use this to prove that every cubic curve or every elliptic curve can be embedded as a cubic curve in P2. The proof is very easy. I don't have time to do it, but I just want to say it's very powerful. It can be classified every lower genus curve using this formula. This is number of genus. Okay. Yeah, I think I'm out. So probably I'll stop here. Thanks, everyone.